Welcome to Modular March. I'm Andy, this is Robbie, and we are the Rollup.
Modular March is an educational experience about all things modular. Enjoy.
Welcome back to today's episode of Modular March, Building the Modular Mindset. Today we have the pleasure of speaking with Felipe Argento from the Cartesi Foundation about modular execution layers. Felipe, thank you for being here and welcome to Modular March.
It's a pleasure, man, and I love the initiative. So today I'm going to speak about modular execution layers, and we're going to explore a little bit the design trade-offs around that. So the idea is to convince you guys of two things. The first one is that execution layers have a big design space, right? So I think it's a shame to explore modular architectures and Appchains and rollups without exploring the design space around execution environment. Luckily, that is changing recently, so we have a lot of teams exploring that design space, which makes me super excited. And the other thing I want to convince you of is that execution layers are very much context dependent, right? So there's no single goat of execution layers. It all depends on what you want to achieve and what you want to do. So it depends on so many factors that I'll go over some of them in this presentation. A quick intro about myself. I'm Felipe. I was actually the first dev lead of the rollups implementation of Cartesi. Now I'm a happy advisor at the Cartesi Foundation. Just random information. I'm Brazilian, but I'm very bad at soccer. And I'm also very bad at designing slideshows. So this part you guys are going to be able to notice probably. And these are my socials. I'm always down to chat. So please reach out. I'm on Farcaster, Twitter, and I also hang out at the Cartesi Development Community Discord channel. Always there answering questions and so on. I was told that I need to speak very slowly this time because I'm a fast speaker. So I hope I'll be able to do that throughout the presentation. And please don't stop trusting me because of my headphones. I'm going to buy new ones in Denver, I hope. So, all right, let's get into it. So really quick, brief update on the modular layer, just some understanding on the modular layers. I'm sure you're all watching Modular March, so I'm kind of preaching to the choir here. But this is the basic depiction of the modular stack, right? You have the classic execution, settlement, consensus, and data availability. And the idea is that these layers are presented, are solved by different teams and different solutions. And you can kind of play Lego on it. So you can try different architectures. Of course, all these definitions, they change very often. And we have so many new layers appearing, right? So we have the aggregation layer coming up already, have governance layer. There's the meme layer, which I try not to underestimate, because like things like ultrasound money and 20 million Bitcoins, they are memes, they're super important. I guess you guys are very much into the meme layer, right? This forms the basic culture of the protocols, which is not to be underestimated. And you'll have like convenience layers, service layers, and so on. But well, I'm sure you guys already know a lot about the modular stack, so we'll focus on the execution layer. That is the current plan. And the execution layer looks very simple when zooming out. It's just basically a state transition function. You have an input, you have a state, you get that state, apply the input to it, and you have an output, right? So it's on Ethereum, you have a block full of transactions. You apply a state transition, you have a new state of the blockchain after processing all those transactions. but also transitions. It also works. So, but the difficult part of it is that this state transition here, the execution layer, depends on so many factors. So here we have this is something that we use a lot in Cartesi to try to explain the power of what we're doing, and it kind of shows the interplay between execution layers and data layers. So in a sense, we're talking about, we call this the cone of innovation. And we're talking about the expansion in the design space when you combine solutions that have high computational capacity and high data availability capacity. And of course, this is just an intuition, but what is interesting here is that you have, as you can see, some places are black, and those are the places in which you're kind of wasting a resource, right? So let's take the far right bottom right side of the graph. You have here Ethereum L1, so you have the processing capabilities of Ethereum L1, and you have a modular DA layer. So basically what you have is like a fuck ton of data. Oh, can I swear? I just did. So you have a ton of data. I blame the movies. I learned my English on the movies. So so you have a ton of data, but you have a very low computational capacity, right? So what are you doing with the data? You don't have enough computational power to really work on it. So it's kind of like a dead design space, right? Same thing with if you have Appchain rollups, but you're using the data capacity of Ethereum. So like you have this machine that is able to compute a lot, but you're stuck to the block size of Ethereum and you're paying Ethereum prices. So it's just like having a supercomputer with a single input, not that useful. But once you start to grow both together, you start to expand the possibilities of use cases for the blockchain, right? So again, this is just an intuition. These are not real applications, like not where they actually fit. But say if you have a EVM rollup with EIP 4844, maybe you have more complex DAOs. If you have Appchain rollups with EIP 4844, maybe you have like some kind of decentralized social network, which is impossible in the lower quadrants, right? Because you don't have enough data or computation on it. And I think the best place on the design space is Appchain rollups or Appchains plus modular DA, right? So you can have like machine economies and complex metaverses and so on. So this is a little bit of showing the interplay between computational capacity and data availability, and therefore also showing the interplay between execution layers and data availability layers.
Just to double click on that, so this kind of shaded region here that's showing this cone structure, it effectively starts from Ethereum L1 in this bottom left corner all the way up into Appchain rollups and modular DA in that top right corner. And basically, like the argument that we're making here is that for computational capacity and data availability capacity, the scale effectively goes from Ethereum L1 all the way to like Appchain rollups with modular DA in terms of the amount of compute and the amount of data availability that these types of designs can make. And basically what you're saying, and this is something that's been kind of echoed, I think, amongst the space, is that different use cases require a different design choice. When builders who are watching this are trying to figure out which solution to kind of launch their application on, this is something that they can kind of consider with regards to these trade-offs.
Yeah, that's a perfect summary, actually. So that's exactly it. Of course, this, as I said, it's a limited view. It's more of an intuition. You could add, for instance, a z-axis talking about privacy, which is also a big design space expansion, because some applications, they require privacy, right? But then I didn't know how to make a 3D graph. It would be very complicated to make. So I didn't add privacy there. But yeah, but that's a perfect summary.
Yeah. Just wanted to understand that. All good.
Perfect. Yeah, so, but it's not only about data layer and computational capacity, right? So now we're trying to zoom in a little bit more into the execution layer and the execution environment themselves. And I'm gonna mention some factors that you would count on, like you'd have to think about if you're either designing an execution layer or choosing an execution layer to launch your dApp or your smart contract, right? Because you can be on the both sides of the issue. I'm on the side of designing an execution layer, though I hope that very soon at Denver I'll be able to code something for it. But yeah, so I'm just gonna go over some things to consider. So first we have what kind of dApp are you doing, right? So we have some execution layers which are specific for gaming, for instance. But are you trying to build smart contracts? Are you trying to host complex dApps? What kind of dApp are you going to optimize to? Because everything comes with a trade-off, right? So if you're optimizing for high composability, then you're going to have a lot of other problems or like things that are going to get limited because of that choice. So how computational, like how much computation intensity are you planning to host on your execution layer? Do you want dApps that perform lots of computations? Or like Ethereum, you just want like simple state transitions, which is the case of most smart contracts, right? What is the preferred programming language? Are users gonna code in Solidity? Are they gonna do Cairo, Rust, Python? Are they only gonna use the syntax of those programming languages, or are they're gonna be able to actually import the standard libraries and the open source code that was written beforehand, right? What are the developer resources that developers are going to be able to leverage? Are they going to be able to have introspection, containerization, right? What kind of tooling will be available to devs? And if you look around the design space of execution environments, you can notice like the different choices on regards to all of these. Another big one is latency tolerance, right? So is composability, instant composability, a must for your application? Or are you okay with latency outside of your dApp domain, right? If you're a DeFi application uh, that's talking to a bunch of different protocols at the same time, maybe you don't have a high tolerance for latency. So maybe you're gonna focus on, say, a shared execution environment with instant communication. But if you're a game, do you really need to talk to things outside your domain that often? Do you need instant communication, or can you have some latency tolerance, right? Is it a shared environment or an isolated environment? So, because when an execution layer caters to more than one dApp at the same time, if they have if dApps share the execution layer, there's so much that you need to think about. And Ethereum has done a great job at thinking about it, and that's why a lot of these rollups and app chains they choose EVM. Uh, but that's a big question as well. I'm almost done. Please don't get bored. So we have the proving system, right? Are you gonna use validity proofs? Are you gonna use fraud proofs? And what kind of fraud proofs? What kind of validity proofs as well, right? And this is one of the most tricky ones, because a lot of people they promise these like crazy execution environments, and they say that they'll be able to prove them after, but this is actually one of the hardest steps, and the ability to prove is related to all the things that we were mentioned beforehand, right? So your execution environment, every choice you make has to be compatible with the proving system that you chose. There's also the financial model aspect of it. Who's gonna be paying for execution? Who's expected to validate the results? Um, so there's a lot here as well, right? Because there's always the attention dilemma, right? The attention economics, which is if no one's cheating, then validators are not like if if no one's if cheating is impossible, then no one's cheating. And then if no one's cheating, then you lose money just by validating, right? It's better for you to accept everything because you're sure that no one's cheating. And then the validators are not checking anything anymore. So then people start to cheat. So it's a very unstable equilibrium, actually. The guys from Arbitrum, they wrote a paper on it about this idea of how to properly reward validators. It's quite interesting. I should have linked it here, but anyway, I'm going on a tangent here. So privacy, how important is privacy? Is it privacy for inputs or just privacy for states? So you have Aztec, for instance. Aztec is an EVM rollup, if I'm not mistaken, but they are they are built with privacy enabled from the get-go, right? So it's a private Ethereum in a sense. It's a quite interesting project as well. So the last one, but it actually ends with an infinite list because there's an infinite choice, infinite trade-offs. Of course, in diminishing importance, right? So just like everything, like you have these basic choices that you need to make, and then the choices differentiate you less and less. But what kind of inputs? Like what is an input like? Because this defines if you're connecting to Ethereum, or if you're connecting to Celestia, or if you're connecting to another data layer, and so on, right? What kind of meta information will enter? Because remember, the execution layer receives an input. That can be a block, right? An Ethereum block, but that can be another kind of input as well. What what does your output look like? Is it like, can you communicate? How do you communicate with the external world? Do you do they just have access to your state, or can you just send messages to different protocols? Can you send a message to Uniswap on layer one? Can you aggregate outputs, or like each message is a single transaction, like is its own transaction, or can you batch outputs? How do you prove those outputs, right? Anyway, I could keep going on and on about about these different choices, right? Yeah.
But these are all choices that, again, that if a builder is trying to choose the type of execution layer that they want to kind of build on, you mentioned that it was kind of going in diminishing order. Like, it starts with what kind of DApp are we trying to build? How much compute power, kind of how much state transitions, and what kind of type, goes all the way through languages and dev resources and basically speed and composability. What kind of environment do you want? Do you want ZK, optimistic, or other, or hybrid? How do you want to basically monetize and incentivize privacy, inputs, outputs, and then it begets us to even keep on going. But again, these are all kind of thoughts that a builder is going to have to answer before even building, right? This is how you go into the landscape of all the possibilities in the modular execution layer stack, and kind of pick, what it is that you're looking for.
Exactly. Yeah. That's both for builders that want to build a dApp and choose what execution layer they want to build on. So like, what do they want to build, and then they match what they want to build with these choices and figure out what execution layer is better for them. But it's also for people who want to build execution layers themselves, right? Because sometimes you think it's like, oh, I'm just gonna build this perfect execution layer, and then you start to bump into these trade-offs, and it's better to have a good mental model beforehand. So just I did say that they're in like diminishing orders, but they're actually not. These are the big ones that came to
Right.
mind when I was defining the presentation. The argument is that you could keep going on forever, but you don't really need to, right? Otherwise, you'd never be able to choose. So I guess you have to figure out what's important for your use case and just mix and match there, right? When I myself am analyzing execution layers, I like to split them into two main categories, which I think in a way are a proxy for many of those choices that I was mentioning before. And now, like, look, I threw some logos here. It's very incomplete. This is by no means a, a good depiction of the landscape. If you want that, go to Andy's Twitter. He posts a lot of cool projects there. So I just threw some around here, right? So you have the Solana VM, which is a shared rollup or a shared execution environment, right? Some people are trying to make the Solana VM into an L2 and settling it on Ethereum. But if even in Solana itself it is a shared VM, right? Same thing with Cardano and so on. And Solana makes some interesting choices. So they have that local fee market, which ties into the financial model that we were talking about. They also have high computation, right? Because they parallelize the EVM, so they are trying to tackle applications with high computation. Again, that comes with huge trade-offs, right? If you take a look at the size of Solana nodes, anyway, so I'm gonna try to be positive about all the projects. So, but you can see there's a lot of trade-offs in the execution environments, and they all make very different choices. You have Starknet, which is the other symbol there, just had an airdrop launch recently. They are ZK shared rollup. So they have their own VM, the Cairo VM, their EVM equivalent, but it's another programming language. It's made for generating ZK proofs. Optimism is just like an EVM, right? They do have the OVM, but it's just the idea is to offer EVM capabilities, and which I'm gonna go over in the next slide. EVM is very good for shared rollups, so we have to be careful when we explore the design space of execution environments to try not to be harsh to anyone because of the trade-offs they chose, right? So I see a lot of people talking about the limitations of the EVM, but the EVM does have a very important place in I believe in the settlement layers especially. The other symbol here is Aztec, which is also a shared rollup with privacy enabled. So trying to tackle those uh, uh, applications. And you can see in the middle there's a division line, and have their Fluent and Arbitrum, because from what I understood, they're both tackling shared rollups and Appchain rollups. So you can launch a single chain for your app, or you can have one chain for many apps. And that's a very interesting choice, because in a sense it increases the potential size of your community. The question that remains is if you're going to be able to reach a good balance, because usually you like to optimize for a use case, right? And when you try to cover too many things at the same time, maybe you cannot choose the optimal path on an optimization route, right? On the Appchain rollups, I put here Cartesi and Dimension. They're both targeting specifically Appchains. I'll use Cartesi as an example later to explain some of the choices. But yeah, so I think this is a very good way to first split the execution layers. Because when you have like a bunch of layers, a bunch of dApps sharing the same layer, there's a security risk there, right? Anyone can deploy code to your execution layer, so you have to make sure that your execution layer can handle malicious applications, right? Even gas metering attacks and applications trying to mess up with another application. And in a way, we've seen some like DeFi exploits in the past, because things were coded in a way that they couldn't handle this kind of crazy application on top, right? So the classic thing was like flash loans. So a lot of applications were coded without taking into account the massive amount of money printing that a flash loan could produce. And then someone deploys an application and just like straight up breaks your application. So it is usually like shared rollups versus Appchain rollups. I think the major trade-off is that on shared rollups you have instant composability, right? So applications can talk to each other very quickly. This bad side effect of that is that they all share the same block space. So you have a competitive fee market. You're limited in the size of the computation that you can perform. You cannot have a different level of decentralization because everyone inherits the decentralization of the whole, and so on. But the composability is great. On the Appchain rollups, on the other hand, you gain a lot of computational power, because in a sense you have this idea of the entire block space to a single application, and there's no one else messing with the demand for your block space other than your application itself. But you have a problem of composability, right? And then the argument is that if you have complex enough applications, then the need of composability goes down by a lot, right? So I chose here 2 examples. I chose to talk about zk sync, and the question is, why does the design choices of zk sync make sense, right? So zk sync is a shared zk rollup. So they have this era VM, which is their execution environment. And it's basically an EVM that knows how to deal with zero knowledge proofs. And the EVM was, as I was talking about, it was made to support competing applications sharing the same layer, right? So they have battle-tested adversarial metering. So this idea that metering can be under attack. There's prime composability built in, so applications can talk to each other super quickly. And the ZK choice adds even more composability, right? Because it's very easy to prove the execution of your execution. It's very easy to prove to other layers and other apps and so on. The computations are small enough that ZK proving is reasonable, because ZK still has a big overhead when proving computations. But they're targeting what's going on Ethereum, right? And Ethereum is not a very high computational chain. So, I mean, the type of proof that they chose, the type of proving system they chose, is compatible with all the choices they made beforehand. And it's optimized for hashing operations, just the EVM in this case, which is 200. So it has 256 bit words, which is a very odd choice for anyone that is building anything other than blockchain applications. But it's apparently great for optimizing hashing operations, right? So I think this is for a very similar reason makes Ethereum a very powerful settlement layer. Just because, I mean, it has enough computational ability to verify ZK proofs and to play fault-proof games, right? So in a sense, you have this one spot in which every layer or every DApp can write their truth, and that can be queried by all the other uh, players in the game, right? So you don't have to just keep asking someone about their state. You can just check at the settlement layer. So I wouldn't sleep on the settlement layer. I know that there's some modular folks who don't like the settlement layer too much. I'm still not convinced. So if you don't like the settlement layer, just maybe come talk to me and we can debate it, and maybe I'll be convinced. But anyway, so yeah, so ZK Sync is you see that their choices make a lot of sense, right? Uh, they thought about what they want people to build on it, and they built an execution environment that targets that. And Cartesi, which is the project that I contribute to, the Cartesi rollups uses the Cartesi modular execution layer uses the Cartesi machine, not just because the name is the same, but because the execution environment makes sense to what we're building. The Cartesi machine is it's a RISC-V based architecture. So the whole idea is that with the extra computation that we get from being isolated, right? So from being an app chain, you gain this entire block space for yourself. You gain this extra computation. So we chose to use part of that computation to boot up this Linux operating system. And the idea is here is to give expressiveness to that developers, right? So we focus on the tooling part of the execution layer. Uh, so we are optimized for computational power. So in order to take advantage of the modular DA, right? So if you have a lot of data, then it's hard to make use of that with the EVM. So if you have a lot of data, maybe you need a very a complex execution environment to take advantage. So we're aiming to allow fairly complex applications. So that's why I have like a file system, and you can use the tooling that a complex app needs, right? Even like files and even databases, if you want. It's kind of interesting that the applications can be initiated with an arbitrary amount of data, right? Since it's an app chain, uh, it you get to choose how decentralized your app chain wants to be, right? So say you're building I don't know, like high-end car marketplace, so people selling like Ferraris and like very expensive cars. maybe you don't want the normal laptop to be able to validate that. You can like assume that people who are browsing a expensive car marketplace will have a very decent computer, or can pay someone to have a very decent computer to validate that application. Though it might be a dumb application, I'm just using it as an example. So you can pick and choose on those requirements, right? And we also have it so that outputs can be aggregated, and outputs are also generic enough that they can target any smart contract, which is a way to deal with this composability problem, right? So since there's a latency on this communication, we chose to have a very generic type of communication so that you can actually like send the message you want in whatever way you want to other layers or to other applications. And then the proving system for what I'm describing is actually quite tricky to design. So we designed this protocol named Dave, which is a fraud-proof system. It's based on optimistic games, just like verification games and so on. But it's specialized for application specific, right? Because you have like, for instance, Arbitrum has their fraud-proofing system called Bode, which was a solution for the delay attack on rollups, which is a very common attack on optimistic fraud proofs. But in their solution, the computational power that you need to fight the attackers grows with the number of attackers, which is very bad if you have an Appchain, right? It's okay if you have a shared layer, because then you can assume that you have enough computational power across the honest nodes in the layer to defend yourself against an attack. But if you have an Appchain, then maybe it's just you against the world, right? And that's where the name of the algorithm comes up. So I'm just trying uh, to convey the point that the fraud-proof system has to be aligned with all the other choices, right? Because if we were to use a very like a out-of-the-box fault-proof system, then we'd be subject to these delay attacks. Or if we were to use ZK in its current state, then I mean you need a very very big computer to be able to prove a single state transition of an application. So I guess that's it. I hope that I convinced you that there's a lot to think about when you're thinking about execution environments. We do have some in-depth explanations of our design choices that I can share later, but there are so many cool ones around, right? So there's so many like very good teams attempting stuff. It's a vertical that is worth following, man. So yeah, I'm
Yeah.
open for questions
Yeah.
on it.
I'm certainly convinced. Thanks for coming on, Felipe. I see Andy has a question. I'll let him start, and then I've got a couple questions myself. So, Andy?
Yeah, I mean, I'll just do one briefly, which is, could you just kind of walk through again with regards to this cone of innovation, and then coming back to the differences in the design choices with like basically a general purpose roll up or execution environment shared in this case is kind of how you named it versus like basically like an app specific or like a isolated execution environment.
Yeah.
Like generally speaking, can you give us maybe like the top 3 or 4 design choices that you think make the most sense for a general purpose or a shared execution shared execution environment, and then like an app specific? Now, I understand kind of specifically with ZK Sync and Cartesi, but perhaps like broadly speaking, like what design choices are generally the right ones for a shared or a general purpose execution environment, and then which are typically the right ones for a app specific or a isolated execution environment?
Yeah, sure. That's a very good question. So when you're talking about like some execution environments, they kind of tell you what they're here for from the get-go, right? So for instance, the EVM was clearly built to allow this shared environment of many dApps. There are some teams that they take the EVM and they just disable the permission for you to deploy a new smart contract, right? So in that sense, they're making an EVM for a single dApp or for a group of the apps. But the general case is for you to have an EVM for a shared execution, right? So what you need to be able to do when you do an execution environment for shared is that you need to make sure that you have very good metering, because when anyone can deploy a new DApp, you have to make sure that the other DApps or the other validators who are validating all the DApps are not losing money by validating the malicious DApp, right? So say, take Ethereum as an example. If I was able to discover that, say, the add gas instruction, so the add instruction costs $5 for me to send a transaction that targets this instruction, but costs $7 for the validator to run that instruction, right? I just found a bug in the metering system. So now I can create an application that just like does a lot of like add instructions, and I'm basically attacking every DApp at the same time, right? So so this metering is a very big thing. I call it adversarial metering, which is this idea that like one can actually come and attack your metering. A very important thing is to have very good, like the apps to be self-contained. So like when you're running Linux, it's kind of hard to control one code of touching another like place in the memory space, right? There are solutions, like we're exploring hypervisors for that and Vert.io, but on the EVM or these shared environments, right? The Solana VM, even Cardano's, they are built in a way that when you deploy a code, that cannot touch the storage of another contract, right? So I cannot just like launch some code that goes and steal Uniswap's money, right? So this like self-containment is quite important in shared layers. I think simplicity, like not simplicity, but the, if you have a shared layer, you shouldn't try to cater to computationally intensive applications. Just because it's same problem, right? As soon as you have an application that is requiring a lot of resources from the validators, either you centralize the chain a lot because now very few people can validate that, or you're paying like a massive price for the block space. On the other hand, for app chains, I guess for app chains, well, first you can do these more computationally intensive applications. You have to cater for applications that are try to cover more ground of a domain. What I mean by that is that, say, like when you launch an ERC20 token, you have to compose that with an exchange, right? Because that's the way, like the only usefulness of like the token itself has no usefulness by itself. It has to talk to other smart contracts to be able to be used. Say it's a governed smart contract or an exchange or a lending platform and so on. When you're doing app chains, it's ideally you try to cover a whole domain of functions, right? So if you're launching an exchange on an app chain, then maybe you should do leveraging there, and you should do lending there, and you should do like staking there as well. So you don't go to this problem of the friction of communicating with other things. But I guess the main benefit of app chains is not only the computational intensity, but also the tooling and the dev resources that you're able to give, right? So now we're seeing, just as Cartesi is experimenting with RISC-V, which is like this battle-tested general architecture, right? That has actually been built by people who are specialists in building instruction sets. There are some projects that are experimenting with WASM as well. So WebAssembly, which also has some interesting trade-offs. I think Appchain is the best place to experiment with that. Experimenting with that for shared rollups is kind of tricky because of these things that I mentioned before, right? Like adding a metering system to WASM, it's gonna be like a very interesting research project, and it's always like ZK proving WASM and so on.
Just it's this idea about like customizability and sovereignty from a app chain approach with regards to having that control and over your execution environment and not being subject to, different teams' choices, which is basically like the land. If you can compare it to like a city on Earth, it's like rather than being subject to your nation state's decisions as to where your office building resides, you just put a big fence up around your office building and call it your own place, your own country. You make the rules, and then there's trade-offs with the isolation with that as well. But I appreciate that answer, and I'll pass it to Rob.
Can I just add just one thing that you made me think of now? So I guess it's interesting to think about this like the fence analogy, because all these things that I said that we should like consider when thinking about the execution environment. If you're doing a shared rollup, then every choice you make on these boxes, they apply to every other application on your nation state, as you put it, right? But if you have a fenced real estate, then you can actually make these choices and slightly tweak the execution environments to appease your specific use case. So this flexibility it's quite big on that, right? So like you can subsidize specific interactions, you can do like these crazy compression tricks and so on.
You have control over taxes, HR, policy, governance, voting, and then you can kind of decentralize and do these types of things based on your own preferences, which is, I think builders are going to opt for that choice quite a bit in the future.
Yeah, I hope so too.
You answered my previous question, so I appreciate that. There was a couple things that I found really, really interesting about the presentation. And one thing that you mentioned now is as builder developers looking at these considerations, if they're building a general purpose or shared environment, when they go through each of these considerations, they have to compromise on every single one because they have to think about all the different types of dApps that are launching on that environment. Whereas an application-specific environment can think about like very specific use cases. They don't compromise for like the middle approach on each of these. They can go, lower latency or more privacy depending on the parameters that they're optimizing for. So I found that really, really interesting. And then the other element that I found interesting was on this cone of innovation, which I think it's a great image, and it's also a great meme. And I think one thing that occurred to me was the shared environments are in the bottom left hand corner because they are optimized for the general purpose, but they have less capacity and less data availability. And then the application-specific environments optimized for the outer edge of that cone, like the more cutting-edge dApps, because they have more capacity and they have more computational capacity and data availability capacity. So I found that interesting. And the last point is that you mentioned if the PowerPoint skills were really on point, you would add a third axis of privacy. And I think you could add, assuming the PowerPoint skills, you could add, 8, 9, 10, an infinite amount of axes, because you really have each of these considerations here where you're going to land on this graph. So I found this map, really, really interesting. And it's going to be really, really fun to see how the cone of innovation continues to expand. So I really like this illustration.
So Rob, you're saying that like basically all of these different things could somehow, in some capacity, no pun intended, be a part of the access here.
Almost. Well, I think so. And Felipe, correct me if I'm wrong, but if you look there at the list, the second consideration we have is computational intensity. Another consideration I think we talked about is data availability. And then we've also got privacy is one of the ones that you mentioned as far as another consideration. So yeah, I do think that each of these considerations, and Felipe, I'm curious if you agree, each of those considerations could make up an axis on this graph.
Yeah, so I mean, I love your comments. I'm not sure if the designer that I'm friends with is gonna love the thought of adding 7 or 8 more axes there. But we do have a very good mathematician. Maybe he'll figure out a way to like the topology aspect of that. No, man, I fully agree with what you're saying. I think I would probably choose to tackle the ones that most impact the design space. So privacy is one that I really do think impacts the design space a lot. But as you correctly mentioned, there are some other ones that, I mean, composability also impacts the design space exploration a lot. And what I find very nice about this kind of innovation is that, as you see, the darker part of it tends to be true about most things, right? So if you had a privacy axis, like what are you going to use privacy for if you don't have data ability or computational capacity? Yeah, you can maybe like say you can put 8 bytes of private data on a blockchain. Like you can't do anything with those 8 bytes. So yeah, feel free
Yeah.
to help me out, guys, to expand this and make it into a real cone. Because I guess right now is a triangle of of innovation.
And that's the best part about this series, man, is that we're going to be able to look back on this in a year, and this cone's going to have tons more of different sectors. I think generally we can expect to see that modular DA category be separated into specific DA layers. I think then we'll see the Appchain rollups category be separated based on WASM VMs, SVMs, Linux VMs, different types of kind of stacks, and then also different settlement layers like Dimension, Ethereum, Solana will have its own rollup soon, and various other ones as well, Anisha and different ones. So all in all, thank you so much for being here and a part of this Modular March series. It's been a pleasure to have you on, sir, and really enjoyed the presentation.
Thank you, man. It's a pleasure. And I'll see you around.
Yes, sir.